In section 2.8, we start talking a little bit more about mass and atomic mass, which is where we look at individual atoms and figure out by the abundance of the different isotopes that might be present for that particular element's atoms, what we can consider to be the average weight that we'll actually encounter when we pick up a sample of atoms. So the issue that we run into with this, why we can't just say, well, carbon weighs exactly this much or nitrogen weighs exactly that much, is we have isotopes present. Right? And isotopes mean we have different numbers of neutrons, and that different number of neutrons means that we have different overall masses. So that's our main first issue here, is that not all atoms of a given element will actually have the same mass. What we do know, though, is we can measure through some specific instrumentation what the relative abundance of each isotope is, and then we can calculate basically a weighted average, and that weighted average is called the atomic mass. And this makes more sense with an example, so let's take a look at an example here. Now, chlorine is listed on the periodic table as having an atomic mass of 35.453 atomic mass units. And we talked about what atomic mass units were previously in terms of number of grams. That's really, really small mass, but we're talking about individual atoms here. Now, chlorine doesn't have an isotope that has a mass of 35.453 AMUs. Instead, we have about 75% of chlorine 35 and about 23, actually it should be 24.23%, sorry about that. That percent of chlorine 37. Yeah, see, I fixed it on this slide. Good. Pressing on. So to find the weighted average of what a sample of chlorine will have, meaning that a large number of chlorine atoms all together weighed up, we'll get kind of an overall average mass, not an average where each of them are contributing equally, but an average where we're looking at 75% one and about 25% of the other. So to do that, we have to find the mass of a chlorine 35 isotope, and by find the mass, I mean experimentally. Don't try and go calculate this. You can add up the protons and the neutrons and the electrons here. You're not going to get the right number. You're not going to get the value of AMUs that you would expect. You're actually always going to get something slightly less, unless you're dealing with a hydrogen 1 isotope. And part of the reason for that, you know what, I'm not even going to get into the reason here. If you want to get into that, feel free to drop by my office. We can talk about mass defect and nuclear binding energies and that sort of thing. But let's just suffice it to say I won't ask you to come up with these numbers. You have to be given the atomic mass of an isotope to work on these problems. So if I have 75.77% of an isotope, though, that has this particular mass, I can calculate its weighted average portion by taking the decimal equivalent of 75.77, that's just taking the percent and dividing by 100, multiplying it by the mass of that particular isotope, and that means that 26.497, we're not rounding yet, wait till the end, but about 26.497 atomic mass units are being contributed to the weighted average just by chlorine 35. Now, chlorine 37 is 36.97 atomic mass units. We are going to do the same process where we multiply that fraction of chlorine 37 times the mass of chlorine 37 and find that this particular species at that natural abundance level is contributing 8.958 atomic mass units to the atomic mass of a chlorine sample. So we just add those two together. What we get is the combined weighted average, and we refer to this as the atomic mass. Okay, so that's how these things are calculated. The abundance times the mass gives a portion. The abundance times the other mass of whatever's present gives another portion. Add those two portions together, and we get the overall weighted average that we use for a sample of those particular atoms. So you give this a shot. Go ahead and pause it, run through the exact same way that we did this before, and see what you come up with. Okay, so what you should have done is take 0.9893, that's the 98.93%. We'll multiply this times the weight of carbon-12, which is actually defined as 12.0000 atomic mass units. And when we do that, we get, let's pull out the calculator, 0.9893 times 12. We get 11.8716 atomic mass units towards the weighted average. So we also have to figure out carbon-13, which is 0.0107 as the fraction. That's 1.07%. You just divide by 100% here. That's how we get these numbers. Times the 13.0034 atomic mass units that carbon-13 weighs. So 0.0107 times 13.0034, and we get 0.1391 atomic mass units. Okay, so sig fig wise, we have 3 here, we have 4 here, so we're looking at 1, 2, 3, 4, 1, 2, 3. So when we add these together, we're looking at the hundredths place, being the one that each of these have a significant figure in. So let's add the two numbers together, and we get 12.009, so we round this up to 12.01 atomic mass units as the average atomic mass for carbon atoms when we consider the weighted average of the isotopes. Okay, so a quick check. Is there any individual carbon atom that has this mass? Nope. They either have 12 or they have 13.0034. There's no in-betweens, there's no partials. It's one or the other, carbon-12 or carbon-13, and a really tiny negligible fraction of carbon-14 that we're not considering here. But no individual carbon has this mass. This is the weighted average.